Assalamualaikum and very good day to everyone. So today we will continue our topics in this electrostatic field chapter, alright, which is regarding on the electric flux density. And when we discuss about the electric flux density, it will relate with the Gauss law. Alright, so today we're going to look into these topics, okay, where previously we have discussed about the electric flux. I hope you guys already remember what is electric flux is all about. Okay, let's look what are the learning overview that you're going to learn in these topics. First, we're going to look at the introduction to the electric flux density, all right, and then the applications of the Gauss law. The applications of the Gauss law in order to calculate the electric field intensity. So I believe you have learned the electric field intensity before, but then you are using Coulomb's law, right? So in this chapter, we're going to use Gauss law instead of Coulomb's law, alright? Alright, so before we continue with the electric flux density, let's have a fast recap on what is electric flux. So if you still remember, electric flux, where the symbols is given as psi E, okay, it is a flux leaving the surface. Okay, flux that is leaving the surface is equals to the charge that is enclosed the surface. So that is what we called about electric flux. All right. Okay, now there's a new term, okay, that will be introduced to you guys, which is electric flux density. Okay, electric flux density, and the symbol is given as D. Okay, and it is, since there is a cross above here, so meaning that I think by now you should know that the D is in terms of vector. Okay, so when we said about vector, it must have a directions and it also have the magnitude, right? So D is represent of the flux density, electric flux density, and so in terms of proportionality, the D is proportionate to electric field intensity. Okay, so as the diagram here shows, okay, the directions of electric field density, electric flux density is the same as electric field intensity. Okay, it has the same directions. Okay, so the lines that coming out from the source, the point charge here, is what we called as electric flux. Okay, so these are the imaginary lines of electric flux that you are unable to see by your naked eyes, but we know that it is exist. Okay, so in terms, if you want to convert from the proportionality into equality of mathematics, we need to introduce one constant, and the constants that we will be introduced is epsilon naught. Okay, so D is equals to epsilon naught E. All right, D is equals to epsilon naught E. All right. Okay, now let's look into this diagram that is shown inside the slide here, that is inside your slides here. So we have a point charge. Okay, so this is one of the electric source. Okay, we have the point charge, and these are the electric flux. These are the electric flux that is coming out from the point charge. Okay, so we know that psi E is equals to the number of charge for this electric source. All right. Okay, we want to measure the electric flux density. Okay, the electric flux density for this structure, or for this point charge. Okay, So we know the electric flux and the charge is in a scalar form, so and the D is in a vector form. So let's convert D into the scalar form. So D, okay, modulus D, modulus D is equals to the total number of charge or flux, total number of charge or flux over A, which is over the distance of this the area of this imaginary closed surface here. Okay, so A here is equals to what? A is equals to 4 pi r squared, right? 4 pi r squared, because this is a sphere, right? So it is equals to, A is equals to, the area we're going to be 4 pi r squared. So if we can substitute inside this equation, okay, if we can substitute inside this equation, okay, your D would then, okay, I'll write it here, your D will then be Q or psi E, right? Q over 4 pi r squared. And if we can see here, your D, okay, if you want to make it into the vector form, okay, the directions of your D, okay, the directions of your D is equals to the directions of your E. So where is your directions of E? So the directions of E will then in this direction, right? It will be pointing out. Yeah, remember, yeah, electric flux is always pointing out from the source. So, and the directions of electric flux is same as directions of electric field intensity. So the direction is pointing out this way. So this is, we're gonna be in directions of R. So that's why when we convert the D from the scalar form into the vector form, it will be in a R direction. Okay, so the units were gonna be, okay, since charge, the unit is coulomb, and area, the unit is meter squared, so it's gonna be coulomb per meter squared, right? Alright, so since that we know already the value of D, okay, where D is equals to Q over 4 pi r squared in R direction. Okay, since that we already know the electric flux density based on the previous equation, we can always determine electric field intensity if we know the electric flux density. So we know that D is equals to epsilon naught E. Okay, epsilon naught E. D is equals to epsilon naught E. So equals to Q 4 pi r squared in R directions. So in terms to find or to determine only the electric field intensity, you can bring your epsilon naught down part here. So it's gonna be Q over 4 pi epsilon naught r squared in R directions. Okay, so the units were gonna be in volt per meter. Alright, so this is another way for you to measure your electric field, or for you to determine, yeah, the electric field intensity, but after by knowing the electric flux density. Alright, okay, now let's look at the bottom part of your slides. Consider a small portion of sphere with radius r, and the surface is given as ds, and there is a flux coming out from the source. So where are the sources? The source is located at the center of the origin, okay, and we need to find the total flux that is passing through this total area of sphere. Okay, and now to find that, we know, yeah, D psi E, okay, a small portion of an electric flux is equals to the D dot ds. And you need to remember that this is a dot product. Okay, this is another formula, yeah, and this formula is using a dot product. Okay, and then from here we know to find the total of the electric flux is given as integrations of d psi e, right, and is equals to the d dot ds. Okay, right, so this is equals to, alright, so your psi here is equals to what? Is equals to q, so therefore we can also represent this in a q, yeah, so q is equals to integrations of d, which is electric flux density dot product with the area of the electric flux density. Okay, alright, and this q, please remember that this q is only the value of q inside this closed area of imaginary surface, and therefore to remember that, we usually rewrite it as q enclosed is equals to integrations of electric flux density dot product with the small area of surface, and this is actually is known as, okay, and this is actually is known as Gauss law. Okay, is known as a Gauss law. All right. Okay, let's look what is the definitions of the Gauss law. So Gauss law is the integrations of electric flux. Okay, it is actually the integrations of electric flux density over a closed Gaussian surface as equal to the charge enclosed the surface. So this is actually an explanations of the equations of Gauss law. All right. So when to use this Gauss law? Okay, when to use this Gauss law? Alright, it is used to find the electric field intensity. Okay, you can use your Gauss law to find the electric field intensity. And Gauss law is a much simpler than the Coulomb's law. Alright, and however, to use a Gauss law, it is not applicable to all. Okay, to all structure, you have to ensure that the charge distribution on that particular surface or structure is a symmetrical. Okay, so therefore you have to ensure this is one of the rule, the symmetrical charge distribution. Okay, and you are able to obtain E from the electric flux density, where we already know this. Okay, where we already know this, which is D is equals to what? Epsilon naught E. Alright, so this is the formula of the Gauss law, which is the close, okay, close as here is referring to the surface, close integrations of the surface of D dot product TS is equals to Q enclosed. So here, if you realize this formula is using the dot product, so you have to remember dot product, dot product. So you have to remember again what is the law of the dot product. Okay. All right. So this is the somehow the what a summary of what we have learned so far. Okay. Let's say that you have a stationary charge. Okay, point charge. For example, the Q. Okay, you have a Q which is a stationary charge. Okay, and from this Q you are able to obtain what we have learned so far. Yeah, you are able to obtain the electric field intensity directly, okay, by using Coulomb's law. However, based on your previous experience with your Coulomb's law that we have learned before, okay, you can find that Coulomb's law is a little bit complex calculations. However, it can be applied for all cases. Okay, you can directly use Coulomb's law to determine the electric field intensity, okay, where the formula is given as such. Alright. However, from today's lecture, you now has been introduced into a Gauss law, whereby using a Gauss law, you can determine the value of D, and once you know the value of this D, you can determine the value of electric field intensity, since that we already know that D is also equals to epsilon naught E. So once you know your D, okay, to know your E, okay, you can just use this equation. Alright. So Gauss law, later we can see that the structure is the calculation is much simpler compared to Coulomb's law. However, it is not able to apply for all cases. There are rules to use Gauss law. So when to use Gauss law? So to use Gauss law, there are four points, rules that you need to remember. Okay, first of all, you have to ensure that the source as a point charge. If the source is a point charge, yes, you can use Gauss law. If it is a line charge, okay, you have to make sure that the line charge is infinite line charge. And same goes to the surface charge. If it is a surface charge, you have to ensure, you have to confirm that the surface charge is an infinite surface charge, and also volume charge. Okay, so volume charge, you can always use Gauss law. Okay, volume charge and point charge, you can always use Gauss law. However, for line charge and surface charge, you need to make sure that it is an infinite structure first, then only you can use the Gauss law. Alright. Okay, now let's look at the first example of the Gauss law. So we have a line charge that you have to remember that the line charge must be in infinite length, okay, of the line charge, and we need to find the electric field. Please add the word intensity here, yeah? Electric field intensity at a distance r from the line charge. Okay, so we have discussed these questions by using the Coulomb's law, if you still remember, and we are able to obtain by using the Coulomb's law the value of E is equals to rho L over 2 pi epsilon naught r on r direction volts per meter. So this is when we use the Coulomb's law, we are able to obtain this. So now we want to use the Gauss law instead, yeah. Instead of Coulomb's law, we want to use the Gauss law, and by using different law, okay, we should able to obtain the same answer. So we now want to use Gauss law instead of Coulomb's law. All right. So first of all, the law for using the Gauss law, or the procedure of using the Gauss law, first of all, you need to draw the, remember, yeah, we need to draw the closed imaginary surface with radius r. Okay, and we have to ensure that this imaginary surface must enclose, okay, enclosing the line charge, must enclose the line charge, okay, rho L. Okay, so our line charge now is rho L, so this rho L must be inside the imaginary surface. So what are the appropriate imaginary surface that we can use in order to suit this electric source, yeah, which is the line charge? So the appropriate imaginary surface that is suits with our electric source, which is the line charge, is cylindrical. Okay, is cylindrical. So we can draw the cylindrical and make sure inside the cylindrical it contains of this line charge. Okay, so these are the cylindrical, and now we can apply the Gauss law. Okay, so Gauss law, if you still remember, the formula is given as integration surface d dot ds is equals to q and close. So now let's divide this into left hand side, and this into right hand side, and we solve it separately. Okay, let's solve it separately. Okay, so now let's solve the left hand side first. Let's solve the left hand side first. Okay, left hand side. So in our left hand side we have integrations surface, closed integration surface d dot ds. Yeah, okay, so d we know already, right? D is the directions of the flux density. Okay, so now what is the directions of our flux density now? Our flux density, okay, so this is the direction of flux density. Okay, so the directions of flux density is equal to the directions of electric field intensity, right? So we know based on our experience, the electric field intensity for this line charge is in R direction, right? In R direction. So it must be in R direction. Okay, in R direction. Okay. Or let's say that you don't know how to decide. The electric field intensity, okay, or the flux density, is always 90 degrees. Okay, it's always 90 degrees to the electric source. Okay, it's always 90 degrees to electric source. So we know the electric source here is line charge, and the appropriate, when we use the Coulomb's law, the appropriate orthogonal coordinate system that we use is in cylindrical, and so 90 degrees to this line charge is going to be in R direction. Okay. Alright. So we know already our D will going to be in R direction. Okay. So so our D in R direction. Next, we need to look the closed imaginary surface. Our closed imaginary surface here. So our closed imaginary surface here is a cylindrical structure. So let's look how many surface of this cylindrical contain. So this cylindrical contains of one, which is one surface which is on the top, second surface that is surround the cylindrical, and third surface that is located at the bottom of the cylindrical, right? So if we can write it separately, so d dot ds will contains of the first surface of the cylindrical. Okay, we're going to be d dot ds, which regarding of the first surface of the cylindrical, plus, okay, the second structure, the second surface, which is d dot ds that is enclosed ataupun surround the cylindrical, right? And surface number 3, which is on the bottom one, d dot ds. Okay, so now we already know our D is on R direction. So for surface number 1, okay, for surface number 1, the D is in R direction. Okay, dot product with the ds, right? So ds on surface number 1. So where is the ds for surface number 1? You need to take any sample, okay, anywhere, as long as the sample is located on the surface number 1. So the ds, okay, the ds will for cylindrical, it can be in R direction or phi direction or z direction, right? So which direction should we choose which regard to this sample? Still remember, we need to choose the one that is 90 degrees to the sample. So this sample, the 90 degrees to this sample, we're going to be in z direction, right? So your ds should be in z direction for surface number 1. Your ds in z direction. Okay, so plus for surface number 2. For surface number 2, your d also going to be, the d is always remain in R direction. Yeah, there's no changes of d. The flux density direction. The ds now for surface number 2. Okay, so take any sample that is located on surface number 2. Okay, so your ds will gonna be on this. For example, we are taking this sample. Okay, so 90 degrees to this. Okay, 90 degrees to this, you're gonna be in R direction. So therefore, your ds will gonna be in R direction, right? So plus surface number 3, which is located at the bottom one. So at the bottom, we can decide that the bottom is actually opposite of the top surface, right? So your D will going to be in R direction, dot product with ds, but now it is located at the bottom, so it's going to be negative Z direction. Okay, so let's recall back the knowledge that we have regarding on dot product. So different direction will give us 0, right, for dot product. So this will going to be will give us 0. This as well will give us 0. So left behind only on surface number 2, that will give us value, because dot product on the same direction will give us scalar value of 1, right? R dot with R is going to give us scalar value of 1. So therefore, okay, so therefore only on surface number 2 will give us direction. It's going to be dr. There's no more direction here, because dot product will give us scalar value. So we just want to know, or we just want to remember that our D in R direction, I just put D and subscript of R here, yeah. So dr integrations of R d phi dz, okay, R d phi dz. So if you solve this, it's going to be dr R, we're going to bring R outside and integrate, double integrations for d phi, and another integrations for dz. And if we solve this, we will get the answer on our left hand side. It will be dr R 2 pi L, right? Z we're going to be the heights, yeah? The limits we're going to be the limits from the height of this imaginary structure. So it's going to be 0 until L. Oh, I forgot to mention, yeah, the imaginary structure here, you can just give the height into any value, yeah. So in this case, I just give it as L, and the radius for this cylinder, I just give it as R. Okay, you can also give other value, yeah. So that's why the dz is the height we're going to be 0 until L, and R is R, yeah, because the radius of the cylinder, imaginary surface, is R. Okay, so for the left hand side, it's going to be dr R 2 pi L. So this is not solved yet. We need to look into the right hand side. Okay, for the right hand side now, shouldn't have any vector up here, yeah. For the right hand side, just now we know it is Q enclosed. Okay, Q that is enclosed inside the imaginary structure just now. Okay, so this is the imaginary structure. So the Q enclosed, we're gonna be this is our source now is a line charge. So Q for the line charge, if you still remember, it's gonna be integrations of rho L dl, right? So Q enclosed, we're gonna be rho L is given as rho L, integrations of dl. Our dl now, it would should be in which direction? We can see the source now lies in what direction? Z, X, Y. It lies on Z direction. So instead of dl, we can write it as dz. Okay, which limit? What are the limits we're gonna be? So the limit just now, we know it must be enclosed. Yeah? Your Q is enclosed. So enclosed in what? Enclosed in your imaginary surface just now, imaginary structure. Okay, imaginary surface structure where the height is given, and which is L, right? The height is given as L. So therefore, the limit will gonna be 0 until L. So if we solve this, your Q enclosed will gonna be rho L, L. Okay. So now if we can equate, yeah, the left hand side with the right hand side. Okay, so the left hand side just now we got it as dr 2 pi rl, and the right hand side just now we are able to obtain as rho l. So if we can solve this, we can cancel the l. Your d will then become rho l over 2 pi r. But then this d is in a scalar form, right? So we know to change into vector form, it must have a direction, and the direction just now we already remember, or we already know that it must be in r direction. So that's why I put it a subscript of r just now, yeah, to remember that our d is in r direction. So the vector will gonna be, okay, rho l over 2 pi r on r direction. Okay, but this is not finished yet, because just now we need to find electric field intensity, right? And electric field intensity, the equation is given as d is equals to epsilon naught E. So now we already know our d, so we can find our E, right? So epsilon naught E is equals to rho l over 2 pi r on r direction. So electric field intensity E will going to be rho l over 2 pi r epsilon naught on r direction, where the unit is volt per meter, and this d, the unit is coulomb per meter squared. Okay, so now you can see the answer that you can obtain, that you obtain using the Gauss law, is same with the one that we use when we calculate using the Coulomb's law, right? So now you have two ways, yeah, to solve. Either you want to use Coulomb's law, or Gauss law, but make sure to use the Gauss law, your structure must be infinite length. All right.